Hey everyone, okay, so I was saying in a video a few more things that we're gonna have to, building blocks as I call them, we're gonna have to go through. That let's start this one, and people who've never studied science kind of step back in horror. Let's talk a little bit about physics. Um, Believe me, you can understand what I'm gonna say. I'm gonna simplify things. We're not going to have to use math or anything. It's the ideas, the concepts is what we need. I've forgotten a lot of it now. Anyway, I mean, if you're not using this stuff all the time, but it's not important. Um, let's take ourselves through the history of understanding. Um, back long time ago, people looked at the natural world, and then trying to understand it, and they came up with all sorts of fantastical theories. But eventually, we reached a point where a perception in science was that there are these things called atoms. I'm sure most people have heard of atoms or elements. You've seen the elemental table with all the different elements: gold, silver, all the different metals. Then there's gases, and so on and so forth. If you want to go and look into that, there was a scientist Rutherford model of the atom, and there was other people. And I'm sure you studied this in school at some point. So they talked about, I think it was called like the current bun model, whatever. So the idea of, you take the solar system, there's a sun, which is what we call the nucleus of an atom, and then the planets are like what we call electrons that are orbiting around, and then the nucleus, or the sun in this case, it can be divided up into protons and neutrons, and this is the nucleus. And you'd have talked about things like the atomic weight. So these things, electrons, protons, neutrons, have what we call properties in physics. So they have things about them that we can measure. One of the things that we can measure is their, you could perceive as their weight, or we say mass in physics or chemistry. Another is the amount of what we call charge. This is coming from the idea of what we call electromagnetic. So what we say, so there's an area of physics developed we call classical physics, and in classical physics we say there are four forces that define the rules of physics, the universe. Hope everybody's still with me here. Just bear with me. These four forces, you've actually heard of all of them. Okay, so there's nuclear, but nuclear is divided into two forces: what's called the nuclear weak and the nuclear strong force. And then the third one is electromagnetic, so think of magnetism and electricity and TV, radio waves, these things. And the fourth one is gravity, which we all know. Okay, so between these four forces, this creates like the rules that govern the properties of these we could call them elemental particles: electrons, protons, neutrons. And then scientists started to ask themselves, well, what happens if we started to observe other, what we could call strange particles other than these simplistic particles. And then you've heard of all these things too. So you've heard of radiation, okay, so X-rays, gamma rays. And then they started to smash these particles into each other, and then that would throw off other, and there's hundreds effectively of these different particles that can be named that spin out of these collisions. So that's what those, you've heard of these colliders, so like in CERN and other places where they accelerate these particles and smash them into each other. This is what they were trying to do. Why were they trying to do that? Okay, well that gets very complicated. Like what they're trying to observe there. They were just trying to build a more complete understanding of the properties of these particles. What is mass? What is charge? And as a result of this, they discovered that actually these weren't the building. So what we really wanted to know is, what is the ultimate building block of our physical rules, if you like. How small can we go if we keep colliding these things and chopping them up? what's the smallest thing that can come out of this? Is there like a particle that is a charged particle or is a mass particle? For example, does an electron have a certain amount of this charge and a certain mass because it's actually made up of special mass and charge particles, for example? That's a question people would have asked themselves back. We're going back quite a long way now, actually, the discovery of this. So, we didn't find a charged particle or a mass particle, but what we did discover is a very, very small other particles. So we discovered from smashing things up, like, what is the smallest thing, and we call these particles point particles. They're so small that you can't actually, so we think of the measurements, you're told there's 3 dimensions when we measure things. With like thinking of a ruler, we can measure it this way, that way, and that way, three measurable dimensions. These particles are so small that they don't have any dimensions. They're one dimensional, okay? So in that sense they do have one dimension, but so we consider them like a point. Imagine a pencil on a piece of paper and you draw a dot, but then you keep making that dot smaller and smaller and smaller, so small that it can't be measured that way or that way. It can only be measured as one dimension, a dot, okay? So the point particles, an electron is a point particle, one of these particles that can't be made any smaller, and something called a quark or quark, depending how you want to say it, is the other one, okay? And the thing that's unique about these quarks is they have a property like electrons have a property like charge and mass, but quarks have a property called spin, okay? And you could think like spinning around. It's not actually what it's not spin like that, but it's sort of like spin, because depending on, if I had a quark here, depending on if you like where you're viewing it from, its spin will make it appear to be all these other particles that we observe. So what we thought in classical physics of all these different particles that we were seeing is actually these quarks just spinning, mostly quarks. There's electrons, there's a few other things as well, and there's things in what we call theoretical physics, things we don't fully understand yet. But basically a lot of them are just these tiny point particle quarks spinning in different ways. Okay, so that's kind of like classical physics. Okay, this is where it gets confusing. Is that I'm going to now tell you that there's this other whole different way of viewing things we call quantum physics. So a problem that occurred we realized that there's something we don't understand correctly in physics to this day, was because the way that when we looked at very small things, how their rules of behavior were acting, we tried to say, okay, if we look at something like a sun or a planet, that must be made up of all these tiny objects, these point particles, ultimately. So if we take the rules of how these point particles are behaving, these quarks and electrons and everything, and scale that up, that should explain exactly how the big objects and everything big that we see. But the problem was, when we went from everything small and we scale it up to everything big, the rules don't agree. Okay, so scientists is the holy grail for scientists, that understand all this far better than I do at this point, because I've forgotten most of it. I used to know all the math and everything when I had to study it, but you quickly forget that if you're not using it day to day. But I studied all these very, very detailed. So they call this, what they want to do is bring the very small and the very big rules together, and this is called grand unification theory. And no one has been able to do this, okay? So we suspect, we say we, but people who work in this field suspect that there's something we still don't fully understand. But a big breakthrough was made with the discovery of what we call quantum physics. So quantum physics is the rules that govern the very, very, very small, these very small point particles and small objects. What we discovered is, well, we'll say we, it's not really we, these amazing people that spent their lives thinking on these things, This was after Einstein. Einstein was still very much in the classical physics model that I'm talking about. And in that model, scientists, including Einstein, believed that if we could just find the building blocks and these rules, that we could literally predict everything, and that the whole, like I said, the example was that the universe would be like a Swiss watch. It's got a lot of amazing moving parts, but we could predict everything that would happen. If we knew where every particle was and these rules, we could predict how they would move. And this is called determinism, the belief that you could predict then, if this is where everything is right now, we could use these rules to predict where it will go next, and so we could literally predict out the entire rest of the universe for all of time. But then came Niels Bohr and other people with quantum physics, and they said, hang on a minute, so these guys have a debate, it's called the Copenhagen debate, where they all sit down and argue out all this stuff, and Einstein wouldn't believe it. The reason being that he had been brought up in this classical physics model, and this was a big shift of perception that was very difficult to make for people in classical physics. That now hang on a minute, I've got news for you guys. We can't predict where every particle is. What? So this threw out this whole idea of the universe being like a clock, like a Swiss watch, and determinism. Because what this quantum physics said was that you can't know. If, let's say, I want to know where every particle is, these quarks and electrons, how do I know where they are? Okay, how do I find them? I have to, it's like your eye. Your eye only sees things because light hits them. What is light? Light is what we know now as these photons, these tiny, you could say particles called photons for the sake of this classical physics. So we have to fire the smallest thing we have. If we fire a big thing to see where it is, like lighting a torch on it, we want to shine a torch on it to see where it is. If we fire something big at it, it would move. So we can't fire big things at these point particles. We need to fire something as small, but preferably much smaller. But there isn't anything smaller than a point particle. So how do we see where they are? If we try to see where they are, like shining a torch, we will affect the position or the speed of it. So you want to know two things. We want to know where it is, and we want to know how it's moving. What we discovered is that because they're so small, there's nothing small enough to tell us that without affecting it. So you might have heard of this. This is called the Heisenberg uncertainty principle. What that's saying is that you can't both know the position and the speed because of this measurement problem. Initially, and I remember when I first studied this in physics, I thought to myself, well, is that just a measurement problem? Is it that if we could find a better way of measuring, we could actually know both the speed and the position? But as we will discover at quantum physics, it turns out no, it's not just a measurement problem. It's actually fundamental to the nature of these small particles, which I'm going to get to, which is quantum physics. I can't explain quantum physics without, I could, but it wouldn't make as much sense to you without giving you this how we evolved our understanding in physics of these very small objects. Okay, so and also thrown in there is the relativity, Einstein relativity, what's called the de Broglie equations. That's also a problem. That's more of a problem to do with speed, and if objects are moving at the speed of light. We'll leave that one out of it for now. There's lots of problems that are just a bit mind-mangling. I often joke that the only person who really understands relativity was Einstein. The rest of us, you can do the math, but we don't really understand it. It's very, very difficult in our minds if we go through that. I'm not sure we need to go through relativity, though people are very interested in things like that. Quantum physics is very important for everybody to understand. So Einstein's basically sat there and said, "What the hell? What are you talking about? This is crazy. Show me, prove it to me." So basically, experiments, very complicated experiments, were done to try to get past this Heisenberg uncertainty, but no one's really. There's some people today that try to claim that they've done it, but they're just, we can construct mental games where we almost fool ourselves in science, but ultimately you can't get around it. It's the same thing as we'll talk about this observer effect. So I'm trying to think where to go with explaining this about quantum physics, because there's several leaps. So that there's actually not one, there's actually two big leaps in quantum physics. So the next big one was this experiment. We wanted to understand, people say, well, all right then, let's use light. Light's a really good one. Light, how is it really working here? Because it's weird, and you do experiments with light, sometimes it acts like a particle, like a tennis ball, think of particles, and sometimes it acts like a wave, like waves in the sea. How can it be both? What the heck is going on here? So maybe we can resolve this argument between the deterministic people like Einstein and the quantum physics, these new people with this new idea, by looking at that. So we create this experiment. So there's a famous experiment with light you would have done in school, we call diffraction. So you fire light at a slit, and you see that it makes like the other side, like areas of dark and light, or we call there's interference going on, so it's acting like waves in a sea. That's how waves behave, not how particle behave. So we're like, well, if light is made up of these balls called photons that are going on a slit, how are they turning into these waves the other side? You know, we need to observe that and see what's happening. And what happened was, the more that the people try to observe that experiment, the more confused they got, because they couldn't observe where light changed, if you like, from a particle to a wave. What they found was when a person, if you like, or consciousness was observing it, it behaved one way, but when a person or consciousness wasn't, it behaved the other way. So this is essentially what is named quantum physics as the observer effect. The fact that the actual act of observing, trying to observe this wave-particle duality, it's called, changes the nature of how it behaves, if you like. And again, scientists will try and debate this. There's a Copenhagen debate for 100 years about this. So I agree with a viewpoint of that experiment, which is called the von Wigner Newman interpretation of the observer effect, which is that what it is showing us is that it is our actual own consciousness that essentially manifests. You could use the word manifest, you could use the word create, use word insert word, that is constructing, or in quantum physics they would say that is what's called collapsing the quantum wavefront. What does that mean? Okay, that's a bit more involved. I will try and explain here of what that means. Okay, so what we say is those point particles, if you're still following me, we're trying to see where they are, right? That's what we want to know. Where is this quark? Where is this electron? We can't directly observe it. What we can do is we can say there's a certain probability that a point particle is going at a certain speed and it is in a certain position, but we can't say for certain that it is there. It's the best we can do. So what we say is that rather than the God created a universe that is made of these particles, and you could know where they are and predict like a Swiss watch, then actually it's more like a universe at the fundamental level where it's like playing dice. And the famous line is, Einstein said, God doesn't play dice. But it turns out for sure God definitely does play dice, and that we cannot for certain, there's only a probability that if a particle, a point particle, is in a certain position. And what this observer effect experiment is saying is that the probability changes effectively according to a consciousness observing that, or the behavior, those measurements could change according to this. So going from a particle to a wave. So you could create an equation for predicting the probability of, like, my glass. Is my glass, if it's made up of millions, billions, trillions of these particles, I could create an equation for the probability that they are there. That's the quantum wave equation. And what I'm saying is that your consciousness collapses or makes, at the point of measurement, that probability becomes 1, becomes that's where it is. But until a consciousness actually observes it, though, the equation is completely different. Okay, it's only a probability, is what I should say. It's not. The probability isn't 1. Some people would even argue that it isn't when you're holding the glass and observing it, but it is very difficult to explain. I'm probably not got that because it's very difficult to explain. So I'm trying to simplify, and I'm probably leaving out some critical things here. But that's essentially it. So in other words, it's our consciousness that if you like, makes real what you perceive as reality, or I would say collapses the quantum wavefront at that point. Until that point, until the observer is there, there's essentially nothing there. There's only the probability of something being there. What? It's very hard for our minds to comprehend that. So I could give you a metaphor for the same idea. That, for example, your television set, like, when you turn on your television set, when you're watching a nature program, that nature isn't actually inside your television set right now. That you are seeing information on that, and it seems to be three-dimensional. If it was even better television for this, it would be like holographic. And you could step inside it and still move around and see it, but you would still know that it was just information being put there. What I'm saying is there's a certain probability that TV program is going to be there at the time that it's meant to be there. But until you actually turn the television on, that point you actually observed it, you made it real, whole. This is essentially what those of us who subscribe to this interpretation of the observer effect believe. This is what that is saying, that it is our own consciousness that is essentially turning that on, that is manifesting that there is nothing here. You are actually not even here, is what I'm saying. Your consciousness is simply shifting and manifesting that information at that point. It's very difficult to get this across, because you could say, well, what is information then? And down the rabbit hole we all go. Okay, and I can attempt to, I've thought on all these things, that I can attempt to, we'll go another layer, but I can't prove these things, because then we're getting into things that science can't prove. Okay, so the next layer of that is, I'll say to you that these point particles, or these the point at which the observer, the consciousness, collapses the quantum wavefront, is a endpoint of a string, like if you think of a string, and if you looked at the end of the string, it would be like a tiny point. Okay, so there's a type of math, a theory that came out called string theory, that says that whilst we perceive 3 physical dimensions and a 4th dimension, which is time, which we can talk about that at some point, time is also a physical dimension. What? Okay, I can explain that. Keep taking photographs and put them out on a table. It takes time to take photographs. You take one every smallest amount of time that you can take one and put them out. You're now seeing them put out it's another physical dimension. Okay, so that we can sort of see in that way that time could be a 4th physical dimension, and relativity kind of proves this, and we could talk about that. But there should be like maybe 9, maybe 11, it depends on the math, dimensions. Well, where the heck are they then? Well, so if you take my string, my endpoint, if you looked at the end of a string and it was like a point particle, what I'm saying is, if you could send a vibration down that string, at the endpoint you would just see this vibration. You wouldn't see where it's coming from. The other end of that string could be these other dimensions. Okay, one of them could be this, what I'm saying is your symphonic self, this other place that your consciousness is, or the observer that is collapsing the quantum wavefront is. Okay, oh, that's a mouthful. I apologize. You might need to listen to this a few times if you've never come across these ideas, and they're not easy to understand, for sure. There's some amazing experiments, by the way, with which I'll try and go across at some point with people trying to get around this observer effect, because scientists don't want this to be true, right? So the other Harvard people who are aware of this will argue that no, this isn't that. What the hell, you're talking crazy. This isn't what that says. It's just a mathematical artifact of math. It's not, it's not what you think it is. Well, that's, to me, it's just their mind not wanting to go there, because if scientists accept this, it's a huge problem for scientific method, because how do we get around the fact that our consciousness is now effectively affecting cause and effect? Everything in science relies on cause and effect, but if our observations can affect the probability of this quantum wavefront, wave equation, waveform, whatever you want to call it, we don't really have any. How can we get around that? It's not like in science, what we do in an experiment, we want to isolate the experiment, but we can't isolate it from our own consciousness, which is what scientists try to do. They try to create experiments to isolate from they're actually fantastical. Some of these experiments are very, very clever, like to try and get around this, but every single time it didn't matter what they did. It was so infuriating. It was like this, like a god. Honestly, it's not what's happening, but it was like the mighty Smiter was just trying to screw with their minds, because, well, when I go through the experiments, you'll understand what I'm saying. It's just crazy, the stuff that happened. Like it could go back in time and alter data and stuff like that. So I am going with this. This is my viewpoint. Other scientists will disagree, but there's a lot of people. I thought Newman was one of the guys that created computing. Amazingly logical person. So it's not like crazy people that believe this. There's a heck of a lot of scientists that believe in the von Neumann-Wigner interpretation of the observer effect. Let's move on. Okay, so there's another evolution of this that has evolved. We could call that's called quantum field theory. So we began to understand from this that, okay, so if it's just probabilities, that where are these probabilities coming from then? So let's take the idea of mass. So this is one that's been in the news a little bit. You might have heard of something called the Higgs boson. So the boson is, a boson is a particle and it's meant. So the Higgs boson was finally the idea of a particle that could give mass to other bigger objects, if you like, bigger particles. But we know now there isn't such thing. Where the Higgs boson, there's only a probability of a Higgs boson. There's not actually a Higgs boson. It's just a probability. Where do these probabilities come from? Oh, they come from the Higgs field. So there are quantum fields. One of them is like the Higgs field. There's other fields that you could think. It's the way I would think of this as a way of explaining it is, so you look at your television set again. You could think of so a television screen is made up of little phosphorus material, and you fire energy through, it's electrons at those the phosphorus to create different wavelengths of light which you perceive as colors. Let's imagine that is a three-dimensional phosphorus. Now we need to extend this a little bit. What the field is like that three-dimensional phosphorus, giving the potential for light to appear at any point in that three-dimensional TV screen. But where did that come from? Where does this field come from? So we have to keep going back. Well, that field, it emanates the entire physical universe. Where did it come from, and how does it emanate the whole universe? Well, okay, now we really sort of getting to the limit of where we are with all this. So the theory, you've heard of the Big Bang, and the idea of that the Big Bang started with a tiny you could think of as a particle, but it's like all the rules of physics and everything and all this. Actually, what it's saying is this is called a singularity, and inside this singularity, so what's outside the singularity? Your mind's saying nothing. There's nothing outside of the singularity. We can't even conceive of nothing. So this is a problem for our mind. It doesn't mean that there isn't nothing. It's just that our minds can't understand that concept right now. But there's nothing outside of it. And inside is these essentially where these fields, the Higgs fields one, and there's other fields, these quantum fields, were in there. So they had the potential as it expanded out like inflating a balloon, it just expanded that potential out, like making the TV, this three-dimensional TV, bigger and bigger and bigger. So instead of seeing it on a tiny, tiny screen, it's getting it bigger and bigger and bigger. And then, now this is where it gets complicated. So then you would ask yourself, well, then why did certain information appear on that TV screen, if you like in the Big Bang? Like, why didn't it just stay these fields with the potential? So that's that you're right. That's the really crazy thing. So in a sense, what a lot of scientists believe is that everything the universe is today was already contained in that singularity. The probabilities, the potential for what it was going to become had to have been contained in there. But our minds, again, can't really, I mean, that's like, what? You're saying this tiny thing that we can't even measure a size, a singularity, quantum singularity, contained all these rules and the potential for all the probabilities of everything that then particles, you perceive it, would manifest and create planets and stars and us, and that's insane. Yeah, that's why Neil Bohr said if you think you understand quantum physics and you think, oh yeah, I got it now, if you're not like falling over and swaying and like, what? I mean, this is madness, right? This is madness. Like, but this is the best understanding we have, and then you could. So it doesn't answer anything about, well, where the hell did that singularity, and how did that singularity have all this? This is so mind-boggling. Doesn't answer that. We can't. Whatever. But I mean, let's say you wanted to design a universe and play it out like a simulation, like I talked about. This would be a hell of a way to do it. It's pretty clever. It's so clever, it's basically beyond our comprehension at this point. But this is really, as best as we can understand it, what is going on. And it's kind of difficult. And I say to people who've not studied, this kind of quantum physics, like, there's nothing really here. Like, what do you mean there's nothing here? Look, there's something here. This is because the bottom line is that we don't know what consciousness is. We can name it, we can call it consciousness, we can see how it's interacting in this observer effect, we can see with it these rules, but because we don't know what consciousness really is, we can't actually observe consciousness. We've tried to observe the mind. I've talked about the mind as a biological machine, etc., etc. But as I've said, we can't. The act of observing changes the result. So the same with our own mind. If we attempt to observe our own consciousness, we're just essentially never going to be able to do that because of this. We probably can make an approximation of it and understand more, certainly a lot more than we do now. And I've said in other videos that I believe we should try and evolve scientific methods around this to try and learn more, observing our consciousness as a way forward. But I don't believe myself that it will ever be possible, because this thing I'm calling the veil, until we have another evolution, as I talked about, manifest another level of evolution of understanding, another layer of this that we peel back to observe our own consciousness. At the point at which we can observe our own consciousness, the artificial veil between this, what we are perceiving as where we are, and this other place where I'm saying you actually your consciousness is really shifting from, that veil will disappear and the two things will merge. But we're not anywhere near that right now. I think it'll be a long time in the future, as far as I can tell. Yeah, so that's kind of a pass through quantum physics. It is kind of mind-blowing. So an example I always like, it's useful, that movie The Matrix, because they sort of pulled together some of these ideas into ways that people can understand. So there was a scene in that movie where Neo goes to see the Oracle, and there's a little kid with a spoon, and I think most people don't understand that scene. I don't blame them. And the kid says, remember, there is no spoon. This is largely, as I interpret it, what they were trying to get across is quantum physics, is that the observer effect, that no, there isn't a spoon, there isn't a glass, there isn't anything. It's your own consciousness that manifests that changes that probability at that moment to something real. So what they were suggesting, the character of Neo, is that you could that somehow, if you truly understood your consciousness, you could change those probabilities, you could change the rules. And what I've said from my own life experience is that quantum manifestation is what that is. So quantum manifestation is possible. You can change the rules, the probabilities, but to a very, very limited extent, which I will discuss at length in my own experiences of this and whatever. You could scale it up to what I've observed in sport. I played a lot of sport and observed people, so you could call it self-belief. Like, why, like in golf, the guy putts the ball and it stops right on the edge for some people, and then it always seems to go in for the guy that has the most self-belief. And the same in every sport I've ever seen. But if that same guy can lose that self-belief, and then his ball always seems to stop. So this is to me a prime example of quantum manifestation. But you can't kid yourself. It's not an intellect. It's not I'll make myself believe, like sitting down with a sports psychologist is what people try to do, and try and engineer this. But it's not something you can do with intellect. It's something that comes from your symphonic self, that you genuinely believe that ball's going to go in there. It's some people will call a knowing. So you can't get around this manifestation issue with intellect. I've experienced this extensively in my life. Like, once you get it and once you understand it, you see it all the time and you know it's a real thing. But here's to understand: it's not like it's a very, very, very small effect, and only and I would say when it aligns with your journey. You can't sit there and manifest, I need $1 million, I'll manifest that. It doesn't work like that at all. And I will try and explain all this at some point. So people have taken this idea and run a mile with it, the idea of, positive thinking, that, just sit there and I want to be famous, I'm going to be famous, or I'm going to make lots of money. No, it's not that. There's no way for that quantum effect to scale up to that. But I have observed it for myself and tried experiments that that we can all experience this effect. So I'm damn sure from that this it's not the truth, but it's close to the truth, that there is nothing here. We are like all our consciousness, whatever that is, this symphonic self, is essentially like putting on a TV set and manifesting information. But the thing is that there's each of us individually, and then there is this collective consciousness and other consciousness. So you could perceive the earth and the universe itself as consciousnesses that are manifesting into this domain, into this TV set, this hologram, whatever you want to call it, collapsing a quantum waveform, probabilities, or there's so many ways we could express it. So it's not just you. So you're you have to be in balance with everything else. There's a limit to what each of us. So that is our journey. If something is not meant to be in your journey, you're never going to be able to quantum manifest it. So this gets deep. So I'm not going to get into this because I was trying to explain the ideas of this in quantum physics and what people are talking about. So when I say quantum manifesting, this is sort of what I mean. I read a lot of Stephen Hawking's work. It was interesting, relates to this. Again, I sort of pulled in string theory, this is just my own ideas, and I haven't talked to other scientists about this, but, I thought a lot about the idea of what is randomness, and is even randomness real, or is that just something, a pattern we're not understanding? You can kind of go crazy with this. I read his work about black holes, and one of the things I think I understood, maybe I didn't get this quite right because it's quite complicated. Stephen was not maybe the best at communicating some of his ideas, that these point particles, like I'm saying, as strings, could also be perceived as being pathways to lose what we call information out of this domain, or gain information. So people ask themselves, well, if something goes into a big black hole, like, where is it going? What I think Stephen was basically saying is you can't, that essentially that information that's being lost has to kind of get recycled back, potentially at any point in any of these point particles. so I said to myself, well, that's interesting, because in that way, maybe randomness isn't randomness. Maybe because without going through some very complicated ideas about chaos theory and butterfly effect, that sometimes a very small effect can scale up to a very large effect, that it would be possible, if what I'm saying is true, for a consciousness to manifest very small amounts of information that had a significant effect in the domain, basically, in this way. I'm not sure how, I think that we can, with science, eventually start to test some of this. People say string theory can't be tested. Um, I think eventually maybe we will get there in some of this, and being able to, because again, how can I isolate if it's an effect of my consciousness? How can I isolate if there's people observing, or even anybody in the world? So it's like, how could you isolate that? People said, like, maybe if we fly, several light years away and conduct that experiment, how far does this observer effect go? We don't know. I think it probably extends forever, throughout the entire domain, unfortunately. So again, this would be the veil. It's stopping us observing what we really are, so we can have this journey, basically. That's getting a pretty out there idea about all that, but that's really where I'm at with thinking about this, about, how can we, with the science hat on, I'd love to be able to get around it and conduct experiments, but right now I'm blocked on that. I don't see how that's possible. Maybe someone else will figure that out. Let's hope. Okay, so that's kind of an overview of some things that I will talk about. So when I say quantum manifesting, that's what I'm talking about. That's not the same. Lots of people will use expressions like manifesting or quantum manifesting, but their ideas are very different, and people tend to overscale that up, like the character of Neo in the Matrix, or just in TV programs and fiction, and that, you have to understand how small these effects would be. If you had, a beach full of sand, and you picked up a grain of sand and changed it to a rock, that's about as much influence as you might be able to have with changing probabilities with consciousness in quantum manifesting. So you would think, oh, well, that's nothing then, that's worthless. Well, as I said, sometimes at certain points, what I call train stations, that can have an effect, that can have this scaled up effect. It's maybe a bit more than that, but it's a lot less than the idea of I can stand there and just manifest anything. And you hear a lot of people in spirituality talking about the source, and the source is providing for you and whatever. This is no, that's not at all my perception. Whatever, you are a source. It's all of your own consciousness as part of this collective consciousness. There is no separate, godlike being or source or whatever. We are all part of this collective. Like I said, like your cells being part of your whole body. So I'll stop this one here, and that's another pass through that, and I'm not sure what we'll talk about next. Well, there's some other big, once we get this understanding of what I'm saying here, it kind of changes everything, the way that we can talk about it. Like when I said about information, so what is information, and information being manifest, like I said, Newton and Leibniz manifesting calculus, or Mozart manifesting his music, that it's coming. So surely that's a much bigger effect. Okay, so there's a lot to talk about there, of what I am saying. I'm saying that essentially that every what you are, this symphonic truth, this symphonic self that we can see somewhat in the observer effect, is essentially a vibration, is a piece of music. That's why I call it symphonic self, that can express here. That's not quantum, it's quantum manifestation, but we're not trying to there's a question of what you are here on your journey to experience, and then what you can change about that journey. That's what I'm talking about there, changing the probabilities. But you yourself, the whole journey is just information manifest in this domain, is a vibration, is, however we want to express it. All right. Well, we'll talk more about that in another video. Okay. Take care.